Hello, Dr. Stewart and fellow students. I am Sebastian Castillo, and I'm going to give you a real-world static analysis of a communal mailbox. This is a photo of the mailbox in question. Here in this photo, you can see a row of 5 12-tenant mailboxes. 3 mailboxes in the middle are the same size, whereas the 2 mailboxes on either end are different from all 5 mailboxes. Uh, all of these mailboxes are made of the same material, which is aircraft aluminum. To simplify the problem solving of this project, I chose to solve the smaller size of the mailbox, specifically as the majority of the mailboxes were the same size, which was the smaller size. Now, here I am presenting to you the free body diagrams, the knowns, and the unknowns. Here is my free body diagram. This is the second iteration of the free body diagram and the best iteration that I have. The knowns I was able to find by going onto the website budgetmailboxes.com, which is where I found the same material, as well as going out and measuring the mailboxes myself with a tape measure. The weight of the mailbox was listed as 129 pounds. Upon measuring and looking at the website, I found the Z to be 61 inches, the X to be 16.5 inches, and the Y to be 30 inches. To simplify things further, I split it into 2 parts, the pole and the box. The pole was 4 inches in the X, 5.5 inches in the Y, and 30.5 inches in the Z, whereas the box was 16.5 inches in the X, 30 inches in the Y, and 30.5 inches in the Z. As for my unknowns, I had to find the force in the X, the force in the Y, the force in the Z, the moment in the X, the moment in the Y, the moment in the Z, and the wind load. Now this is my force equation that I used to find the forces in the X, the Y, and the Z. Here you can see that force resultant is equal to force position vector, which is equal to force of R over R, which is equal to force times XB minus XAI plus YB minus YAJ plus ZB minus ZAK, all over the square root of XB minus XA squared plus YB minus YA squared plus ZB minus ZA squared. Plugging in everything, the force is 129 pounds times 30.5 inches minus 61 inches I plus 5.5 inches minus 30 inches J plus 4 inches minus 16.5 inches K, all over the square root of 30.5 minus 61 squared plus 5.5 minus 30 squared plus 4 minus 16.5 squared. After everything is said and done, I simplify further, which is equal to 129 pounds times negative 30.5 inches in the I plus negative 24.5 inches in the J plus negative 12.5 inches in the K, all over the square root of negative 30.5 squared plus negative 24.5 squared plus negative 12.5 squared. And then the square root further simplifies to 41.1. These are all 3 significant figures. Now the forces in the X and the Y and the Z come out to negative 95.8 I times and minus 77 J minus 39.3 K pounds. As for moments, I use the equation moment about point O is equal to force times the distance. So the moment about point O x is equal to 95.8 times 4, which is then equal to negative 383.2 pounds per inch. Moment about point O y is equal to negative 77 times 5.5, which is equal to negative 423.5 pounds per inch. Moment about point OZ is equal to negative 39.3 times 30.5, which is equal to negative 1,198.65 pounds an inch. As for wind loads, I was able to find an equation on wikihow.com. Here you can see force is equal to area times wind pressure times drag coefficient. To find area, you use length times height. Wind pressure is 0.00256 times the velocity squared. And drag coefficient, for here I use the drag coefficient of a small plane, as that's what a mailbox is, which is equal to 1.4. Now here I have the average wind on a windy day, which is equal to 8.9 miles an hour. So for this equation, it was 30.5 times 4 with the size, the dimensions of the pole, times 0.00256 times 0.89 squared times 1.4, which comes out to 34.6 pounds. Then for 8 miles an hour, same thing, comes out to 28 pounds. 11 miles an hour, the average high comes out to 52.9 pounds. And then the windiest day recorded in El Paso was 84 miles an hour. And that force came out to 3,085.2 pounds. Conclusion. On an average windy day, 8.9 miles an hour, the mailbox will stay rigid. On a day of 8 mile an hour wind, the mailbox will stay rigid. On a day of 11 miles an hour per mile per hour winds, the mailbox will still stay rigid. And on the windiest day recorded, 84 miles an hour, the mailbox will fail. And then these are the list of my references. Thank you for listening.